Welcome my friends, welcome to my next lecture. Now in my last lecture I have introduced the notion of what is called power series. Okay, then also I have introduced the notions of what is called radius of convergence, then we will have domain of convergence, but on the domain of convergence means on the boundary of the domain of convergence, I said that I will give some couple of examples where you will see I do not have any concrete conclusions. So for today's lecture I will start with those examples, then I will move forward for a couple of properties of power series, and then I will talk about that once I have a power series around a point, then it will introduce what is called analytic functions and vice versa, and then we will have Taylor series and Lorentz series. Okay, so my plan for today's lecture is to start with some examples so that on the boundary of the domain of convergence we will see I do not have any concrete conclusion. Okay, so as I said, so on the circle, that means on the boundary of the domain of convergence, as I said, what sort of conclusion I should say. Okay, so that's what I have written. So on circle, see where mod of z minus z naught is equal to r, then what I can say. So you see, on the circle z minus z naught is equal to r, power series may converge on C or diverge on C. See, I don't have any concrete conclusion, or converges some part of C or diverges the remaining part. So that means there could be anything, right? There is no kind of concrete. Like for example, inside the domain of convergence, I have a what is called pointwise convergence. Outside it diverges. Like this kind of concreteness I had it. So it is the inside the domain of convergence and outside. But on the boundary, it could converge, it could diverge. Some part it could converge, some part it could diverge. So one has to examine case by case. For example, that's what. Look at the power series z to the power n. Now it diverges at all points on the circle mod z is equal to 1. Now if you remember, when I dealt with this kind of series of functions, you say that mod z is less than 1, it converges absolutely, right? Or it converges pointwise, and mod z is greater than 1, it diverges, and mod z is less than r, lesser equal to or strictly less than 1, it converges uniformly. So 1 is the radius of convergence. Well, you can say that what is the radius of convergence? You just calculate it. So what is your n here? So for this sequence, what is n? N is 1, constant sequence. So this is a convergent sequence. So therefore, if I consider mod n to the power 1 by n, this is a constant sequence 1, it converges to 1. So therefore, lim sup n mod n to the power 1 by n, this is 1. So the radius of convergence is 1. Inside the radius of convergence it converges, outside it diverges, I already said, but on mod z is equal to 1, this actually diverges. Why? Because if mod z is equal to 1, if converges, if I have a convergent power series, then nth terms would goes to 0, right? I already said as an like properties of convergence of a power series. So now if I consider the series z to the power n from 0 to infinity, and if mod z is equal to 1, then that means what? That means mod z to the power n, this is mod z to the power n, this is 1, and this is true for all n, which is not converging to 0. So therefore the series sum over n from 0 to infinity z to the n, it diverges at all points on the what is called boundary of the domain of convergence. So boundary of the domain of convergence is mod z is equal to 1, and on the domain, since modulus of zn does not tend to 0 as n approaches to infinity, so therefore my series diverges. Consider this power series z to the power n divided by n. What is the radius of convergence? First you check what is the radius of convergence. Now n is equal to 1 by n, right? So now you calculate the limit. Cosines of that will be, as I said, it's very easy. So modulus of n divided by n plus 1, that means you will have n plus 1 by n. And what is that limit? Limit n 1 plus 1 by n, that is 1. So that means r is equal to this. That means radius of convergence of this series, this 1. So now if mod z is, so because this is a power series around the point 0. So therefore what is the what is called disk of convergence, that is a domain of convergence z minus 0 strictly less than 1, right? So therefore by theorem you can say that mod z less than 1 it converges absolutely, mod z greater than 1 it diverges, but what will happen? Mod z is equal to 1, because I already talked about like this theorem. So if this is less than r, that means inside the domain of convergence we will have converges absolutely, outside it diverges, and if I take a smaller closed unit disk, then it converges uniformly. So therefore since the radius of convergence of this power series is 1, so if I take mod z is less than 1, it converges absolutely, mod z greater than 1, it diverges. But now question is what will happen? Mod z is equal to 1. Now you will see If I take z is equal to 1, then what kind of series this is? This boils down to the series sum over 1 by n, and this diverges, I know. So this series diverging series 1 by n series diverges, so this is infinity. So therefore at the point 1 it diverges. Now if I consider z is equal to minus 1, because 1 and minus 1 both are in the boundary of the domain of convergence, that means if I take z is equal to 1 comma minus 1, mod z is 1, that means it is on the boundary of the domain of convergence. At 1 it diverges, at minus 1 what series it is? This series should be minus 1 to the power n divided by n from 1 up to infinity. And what kind of series? This is alternating series, right? So this should be first is 1, then minus half plus 1/3 minus 1/4. So this is a Leibniz series, you can have it, alternating series. From there you can conclude that this converges series, right? So 1 by n diverges, but if I consider that series 1 minus half plus 1/3 minus 1/4, that means alternating series, this alternating series actually converges. So therefore at one point it diverges, but at the point minus 1 it converges. But it says that one can show that this power series converges at all points on the circle mod z is equal to 1 except the point z is equal to 1 using Picard's theorem. So in next slides I will have the Picard's theorem. When I will apply this theorem, you will see this power series, it actually diverges at one point on the boundary of the domain of convergence, but all other point on the boundary it actually converges. Now look at this power series. Okay, what is the radius of convergence? You just calculate radius of convergence, it is actually 1, because what is your n? N is 1 by n square, right? So that means r, which is by ratio test, limit an divided by n square, that means n plus 1 whole square divided by n square, that means this is 1. So this is limit n plus 1 by n to the power square, and what is this? This is 1. So therefore r is 1. So therefore outside mod z greater than 1 it diverges, inside mod z less than 1 it converges absolutely. On the boundary what is happened? On the boundary you see, look at this point series. So on the boundary, so that means n from 1 up to infinity absolute of zn by n square. So this is same as n from 1 up to infinity mod z to the power n divided by n square, right? But mod z is equal to 1, so therefore this is actually less or equal to exactly equal to 1 by n square. But 1 by n square is a convergent series, so this is convergent. So therefore on the boundary mod z is equal to 1 at each point on the boundary of the domain of convergence, this power series converges. So now I have 3 examples. So in one example, at all the boundary point of the domain of convergence it converges. In one example, at one point it diverges, but other point it converges. And you have one example at each point it diverges. So therefore I do not have any conclusions on the boundary of the domain of convergence. So inside I will have the absolute convergence, outside I will have the divergence, but on the boundary I do not have any concrete conclusion about the convergence of the power series. So this is a kind of another Picard's theorem. Using Picard's theorem, as I said in my earlier example, if I have z to the power n divided by n, so this kind of series you can conclude. For example, if I consider the power series, say n z to the power n, power series around the point 0, suppose your coefficients n's are non-negative real numbers, these are decreasing sequence. If it converges to 0, then your power series converges at all points on the circle mod z is equal to 1, except possibly z is equal to 1, so its radius of convergence is at least 1. Okay, so therefore it says that it converges at each point on the circle mod z is equal to 1, except possibly z is equal to 1. Now if I just consider this example, z to the n divided by n from 1 up to infinity, what is your n? N is 1 by n. Now you see this sequence n, it converges all the properties. These are non-negative real numbers, these are decreasing, this converges to 0. So therefore this power series actually converges at all point mod z is equal to 1 except z is equal to 1, because if z is equal to 1, this series becomes sum over 1 by n, and this diverges. Okay, so therefore this is again by Picard's theorem you can have. So earlier I just said that take z is equal to 1, it is the series 1 by n, it diverges, and if I take z is equal to minus 1, then it is the alternating series, it converges. Then I said that, well, actually it converges at all point on mod z is equal to 1 except z is equal to 1, it actually follows from this state. So I have written using the above theorem and using the fact that 1 by n diverges, one can conclude that this converges at all point mod z is equal to 1 except the point z is equal to 1. Okay, so using Picard's theorem you have the full conclusion about this observation. So now this is another, I think this in the what is called calculation purpose or computing purpose, this kind of things might be useful in your exam or in your tutorial, you see if I have a power series with gap. So now earlier I have a power series an, say z minus z naught to the power n from say 0 to infinity. That means it's taking value 0, 1, 2, 3, 4, so on so forth. That means I am not saying that so n starts only on the odd integers or even integers, not or even numbers or odd numbers. Like n is taking value say 1, 3, 5, 7, or n is taking value 2, 4, 6, 8. So but I am saying that power series means it takes all the values. I mean n starts from 0, 1, 2, 3, everything. Power series with gaps means there should be a gap. That means it can take value say like 2, 4, 6, there is a gap. From 2 to 4 you will have 3 is missing, 4 to 6 5 is missing, 7 to 6 to 8 7 is missing. So there is a gap. So that's why this is power series with gaps if I have it. Now in generally how I define it, I am saying that start with a sequence lambda n is an increasing sequence of non-negative integers. So that means your sequence lambda n 0 to infinity, it's inside n from 0 to infinity. It is an increasing sequence such that lambda n approaches to infinity. If whenever n approaches to infinity, then if I consider the power series this, so I have n, I have z minus z naught, everything is there, just power n I am replacing by lambda n. For example, if I take lambda n is equal to 2n, n from say 0 to infinity. So that means what are the sequence, what are the points it's taking? It is 0, then 2, then 4. That means it contains only the even powers. That means z minus z naught of constant 1, then z minus z naught square, then z minus z naught 4, so on and so forth. I mean there is a gap. Odd power it is not taking. So this kind of series is called the power series with gaps with a radius of convergence r. But there is a different formula. What formula? So if this limit, that means earlier you will have n by n plus 1 to the absolute, that's it. But this time if I have a radius of convergence r, suppose if this limit exists, and what is the limit? Of course it is in terms of ratios, that means it is n divided by n minus 1, but you should look at in the exponent you will have 1 divided by lambda n minus 1. In other words 1 by r you will have this limit if this limit exists. Okay, so this is the formula. It says that suppose this limit exists, then your radius of convergence formula is 1 by r is exactly equal to this limit. Now you see this limit is little bit complicated, right? Okay, so this is like r is equal to limit mod n minus 1 divided by n, but you will have some exponent. Okay, that is very important. So therefore if I have a power series with gaps, and suppose this limit exists, then you have the formula for the radius of convergence, but in that case the formula is this one. That means it's a limit n divided by n minus 1 absolute, then the exponent should be 1 divided by lambda n minus 1. So this formula might be useful because you see in the problem or in the say maybe in the tutorials or in the assignment I give some kind of problem, there you will see by identifying the power series you can think about, well it misses like some exponent, it not contains all the points of like natural numbers including 0, like 0, 1, 2, 3, everything. Maybe it has some gap. Now if I have a power series with some gaps, then this is the corresponding formula to calculate the radius of convergence. One example, let me just talk about that. So this is the example. For example, if I give find the radius of convergence of this power series. Now look at the power series. What is your n? N is 1 by 2 to the n. Power series around the point z naught, but look what power it is taking. It is taking the power n square. That means it is taking 0, then 1, then what? Then it is taking 4, then it is taking 9, then it is taking 16. So therefore there is a gap. So that means it is not taking 2, 3, it is not taking the point 5, 6, 7, 8. So there is a gap. So this is actually the what is called power series with gaps. Now if I want to say that calculate the what is the radius of convergence, then the earlier formula like the in terms of lim sup or in terms of lim sup or limit of the quotients of, it will not work. So that the formula is different. Now since it is a power series with gaps, so therefore you have this formula 1 by r. If r is the radius of convergence, n by n minus 1, you will have to have this one. So that means first you have to identify what increasing sequence you will have. So here your lambda n, which is n square, this is my sequence. So then you have to calculate this limit. So what is your n? N is 1 by 2 to the n, n minus 1 is 1 by 2 to the n minus 1. So n divided by n minus 1, which is 2 to the power n divided 2 to the power n minus 1 divided by 2 to the power n, and you have to just calculate 1 by lambda n. Lambda n is n square, then n square minus n minus 1 square. If I do some algebra, it turns out that it is limit n approaches to infinity half to the power 1 by 2n plus 1. Now if n approaches to infinity, 1 by 2n plus 1 goes to 0, so therefore this is 1, so therefore radius of convergence is 1. Okay, so therefore this is one of the easiest way to have the radius of convergence of a power series with gaps. So this is another example I have given. So this is what is your lambda n here. You can easily get what is your lambda n. Lambda n is 2n plus 1. And this is my n. What is your n? N is minus 1 to the power n divided by 2n plus 1 factorial. Okay, so you just calculate it. So I am not doing it here. If you calculate it, then you will have the what is called radius of convergence of this. Anyhow, I can do that. I think yes, okay, do that. Okay, okay. So that means calculate it 1 by r. So limit n approaches to infinity, absolute n is there, so therefore n is, so n minus 1 to the power n, so forget about it, I am taking the modulus, so therefore it should be a suffix n minus 1, right? So if I have n minus 1, that means this should be 2n minus 2, that means 2n minus 1 factorial, so therefore it should 2n minus 1 factorial, right? And n means this is 2n plus 1 factorial, right? This is, and this to the power 1 by lambda n minus lambda n. What is lambda n? 2n plus 1. So therefore this should be lambda n minus lambda n minus 1, right? That means this should be 2n plus 1 minus n minus 1 means what? 2n minus 1. That means this should be 2n plus 1. So that means this should be 1 by 2, half. I mean this should be limit n approaches to infinity 2n minus 1 factorial divided by 2n plus 1 factorial to the power half, I think. Okay, so what is that? So now you see, you just use a factorial formula. So that means 2n plus 1 factorial, and this should be limit n approaches to infinity. So this should be 1 by maybe 2n plus 1, then 2n, and then 2n minus 1 factorial, 2n minus 1 factorial, 2n minus 1 factorial get cancelled. This to the power will have half. Now limit n approaches to infinity, this is goes to 0, so therefore this is 0. So 1 by r is 0, so therefore what is the power series? Power series is, I think this is what? Infinity. So radius of convergence r is infinity. And you see, you can have it. Why is that? If you just look at, this is the radius of convergence of this power series. Now later on you will see this power series, what is the, this power series means what? Radius of convergence is infinity. That means at all point in the complex plane it converges, and it will give you some sum functions. And what is the sum functions? You can identify these sum functions. I think this is nothing but sin z. You just check it, okay? So this is nothing but the series expansion of sine functions. Now sine function is an entire function. It is converges at all point in the complex plane. That is why this series has radius of convergence infinite, and which is exactly the case, okay? So this is nice. So therefore this, though it is given as an exercise, but I have proved it. But in exam or in a tutorial, you can expect, if you identify that you have given, or you are given what is called power series with a gap, then you have to use this formula to calculate radius of convergence. Couple of properties, I'm not going to prove it, okay? So for example, if you have two power series n and n z minus z naught to the n, sum over bn z minus z naught to the n, then sum is also a power series. This is the sum, and its radius of convergence is the greater or equal to minimum of radius of convergence of each individual r1, r2. If I have a scalar multiplications, radius of convergence will be same, because it follows from the straightaway definitions. Because if I what is your bn? So if I scalar multiplication means you have bn is equal to lambda n. So this is the kind of coefficients, but what is the formula? So if I assume that R2 del is the radius of convergence after scalar multiplication, what is that? This is limit n approaches to infinity, limit of bn by bn plus 1, right? I think this is 2. Let me just check, I forgot. Bn by bn plus 1, right? But what is that? This is limit n approaches to infinity. What is bn? Lambda n divided by lambda n plus 1. Lambda lambda get cancelled, so therefore this is limit an by an plus 1. And what is that? This is the r radius of convergence of the series r1, sorry r1. R1 of the series, this one, so therefore R2 del is exactly equal to R1, or R is equal to R1. So therefore this is okay. Similarly, sum also you can prove that radius of convergence is greater or equal to. If I take the product, well, two ways you can define. So if I have two power series, then I am defining a new power series Cn, where Cn is of the form, because I have the coefficients n, I have the coefficients bn. So I am writing Cn in terms of n and bn, which is sum over ak times bn minus k. This is called the Cauchy product. So that means you out of two power series, you will have new power series Cn z minus z naught to the power n, where Cn is of the form k from 0 to n, ak times bn minus k, that is called the Cauchy product. And this is also a power series, and you can prove that it has a radius of convergence r, which is greater or equal to minimum of r1 and r2. I am not proving it, I am saying the properties, okay. But you should kind of convince yourself by discussing with some books and literature. You can have this kind of proof of this kind of properties. Product, just pointwise product, right? This is called the Cauchy product. That means out of two power series, we will have sum over Cn z minus z naught to the power n, where Cn has this kind of formula. But if I just take a pointwise product, that means I have n, I have bn, I am considering new series which is n times bn z minus z naught, then it also radius of convergence, say that it be r, which is greater or equal to r1 times r2. So this you should prove it. Division you can have it. So if bn is non-zero, if I have two power series, then if I have new power series n by bn whose coefficients, and also radius of convergence you can prove it, r is greater or equal to r1 by r2. And divisions of two power series, that means if r is the largest number, such that this power series is non-zero, that means bn z minus z naught to the power n is non-zero for all z in this domain, then I can make sense of sum n divided by sum bn, because in a denominator I am having sum over bn z minus z naught to the power n. Now I have the meaning of this object only when this denominator is non-zero, that I am saying this is non-zero on this domain. Therefore you can have the power series here, and this has a radius of convergence which r is greater or equal to minimum of r, capital R1 and capital R2. Okay. This is another result of power series. What is that? You see, that is another nice observation. If I have a power series, suppose a power series around the point 0, and suppose this power series converges at some point z naught, then it converges at all point mod z less than z naught. That is important. So therefore, if I know this power series converges at least one point, then it converges for all point mod z where mod z is less than z naught. So the proof is very nice. So suppose this converges, so therefore it follows from the hypothesis that there exists a m such that this should be true for all n, right? And why is that? Okay, so let me just prove it. So this converges for some, so that means this is converges n from 0 to infinity. What is that? This is a n z naught to the power n. So this is converges, right? So now since this is converges, so then what can I say? So if a power series converges, this series converges means what? Nth term goes to 0. So therefore you can say that limit n approaches to infinity, n z naught to the power n, this is 0. Now if this, that means this sequence a n z naught to the power n, this is a convergent sequence converging to 0. Now if this converges to 0, then it is a bounded sequence. So therefore it says that there exists a m such that I can have a n z naught to the power n which is dominated by m for all n. Okay, that I can have it, because at some point z naught this is converges, which implies that nth term goes to 0, which implies that my sequence converges sequence, then that convergence sequence is bounded. So therefore I will have a single m such that this is dominated by m for all n. Then what I am doing, I am estimating n z to the power n, which is n z naught to the power n, then z by z naught. So I am just multiplying z naught and taking the division. So that means I am saying that a n z to the n, which is same as a n z naught to the n or z to the n, then z naught to the n divided by z naught to the n. You can have it because z naught is non-zero. Well, z naught is non-zero, so for somehow I think there you needed z naught is non-zero. I assume it, okay. If this is the case, so then what will happen? Then if I take the a n z naught to the n, which is a n z naught to the power n, then z by z naught to the power n, because it follows from here, right? So this object, so if I have this times this, now you see n z naught to the power n, it is bounded by m for all n. So therefore I can say that this is m times modulus of z by z naught to the power n. But you see, if I assume that mod z is less than mod z naught, so therefore what is this? This is mod z by z naught, which is strictly less than 1. Then if it is strictly less than 1, then what can I say? I can talk about the what is called comparison test, or like Wester's M test. So therefore I can say that sum over a n z to the n, which is dominated by m times sum over z minus z naught to the power n, and since z by z naught is strictly less than 1, so therefore this is convergent. Because the geometric series, now if I have a z to the power n, right, sum to the power n. So since z minus z naught is strictly less than 1, so geometrics this I know. So this kind of series converges if mod z is strictly less than 1. So therefore this is converges, okay, and since the right hand side converges, so therefore the left hand side converges. So therefore this is a very simple application of Weierstrass theorem to conclude that if I have a power series an z to the power n, if it converges at one point z naught, then if I take any complex number whose mod is strictly less than modulus of z naught, then at that point also it also converges. So therefore that's the proof. So therefore this sum is dominated by m times this sum, and since z by z naught that absolute is strictly less than 1, so therefore this series actually converges, okay, because it follows from the geometric series, right? If I have a sum over z to the n, if mod z is less than 1 this converges, mod z is greater than 1 it diverges. Since z by z naught it is a single complex number whose mod is strictly less than 1, so therefore this is convergent, and since the right hand side converges, so therefore the left hand side converges. So therefore this is true. This is very nice actually. So that means if I know the convergence at a one point, then I know the convergence at infinitely many points. So that's what it is. Okay, so now, so these are all properties. Now I am going to have this beautiful question that what can we say about the sum functions of a power series. Now you see, I talked about power series, I say that it is series of functions, then I talked about domain of convergence. Now once I talked about domain of convergence, you see if I have a power series n z minus z naught to the power n from say 0 to infinity, and suppose it has a power, it has a radius of convergence r, then if I consider this set B R Z naught, the notation I have written. So this is nothing but all those z in C such that z minus z naught is strictly less than r. Na? So this is the domain. So therefore, if I draw a picture, this is my z naught, this is radius r, that is it. Now inside this domain at each point it converges. So therefore at each point if I take a z from say B R Z naught, so therefore this series sum over n from 0 to infinity n z minus z naught to the power n converges. Convergence means what? That this will give you some complex number. So therefore for each z it will give you some function. So that means what I am trying to say is that if I take z from B at z naught, then this object a n z minus z naught to the power n from 0 to infinity, it will be some complex number. So let it be say b suffix z, some complex number. It depends on z, because if I changes z, the corresponding value will changes because sum will changes, right? So now what I'll do, now I am defining a map. What is that map? This is B R Z naught to C by saying that take a z from the domain of convergence, then this power series converges because of that theorem, because r is the radius of convergence. Then I am saying that z goes to f of z, which is nothing but b suffix z, which I also can write as a n z minus z naught to the power n. So therefore if I have a power series, it will have a sum functions, that is the functions f on the domain of convergence. So therefore if I have a power series, if I have a domain of convergence, then I can define the sum functions. What can I say about the sum function? This is the sum function shape. Now since it is a function defined on the domain of convergence, then I can talk about its analyticity, its differentiability, whether this function, it is a function, right? Now then I can talk about, since I am dealing with complex valued function on some nice domain, then I can say that is that function is analytic, is that function is differentiable, is that function is continuous. So those kind of questions I can talk about. So that is why, what can I say about the sum functions given a power series? Because once I have a power series, it will have a radius of convergence on the domain of convergence, sum functions make sense. Then what can I say about its analyticity, differentiability and continuity? Okay. So that's the target. So let us denote the sum functions of this series by f of z. So this is nothing but f of z is nothing but this object. So that means for each z, I am saying that f of z is the value. What is the value? You put z in this series and wherever it will converges, that value is the corresponding value of f of z. So therefore each power series will have a sum functions, and this is the corresponding notations. F of z is equal to n from 0 to infinity a n z minus z naught to the power n, and of course z should belongs to this domain of convergence, because while I have discussed the power series, there is a theorem that says that for each power series you will have a radius of convergence. Inside the domain of convergence, my series converges absolutely. That means for each z in BR of z naught, it will give you some complex number. So therefore I can have the sum functions f of z. Now these are the questions I am interested in. What is the sum functions fz is analytic? Because I am dealing with the functions, I can say that well it is analytic or differentiable on this set, number one. Number two, is the series formed by term differentiation? That means, you see, in the series, what are the series of functions? it's a series of functions fn, but how the fn looks like, it's a polynomial, n times z minus z naught to the power n, but polynomials are infinitely many times differentiable. So what I'm doing is that now I am starting with this series, then I am forming another power series. What is that? This is nothing but the derivative of this term. That means n times z minus z naught to the power n minus 1. Now this is another power series whose coefficients is different from n, it is n times n. Then I am saying that is the series formed by term wise differentiation, that means I am taking the derivative of this term, making a new series, will it converge? If it converges, what can I say about this radius of convergence of this new series? And is there any relations between the radius of convergence of this series and the series I started with? So that is why. What is the radius of convergence R star? Is there any relations? So this is one. Now once I have this series, then of course it will have a radius of convergence. It will also have a sum functions. I am saying that suppose G is the sum functions of this series, derived series. Okay, by taking 1 times differentiations of each term of the original series. So this will be a sum functions, will sum, and Z belongs to radius of convergence of this series R star. Now the question is, since I am starting with some series, I am taking the differentiations of each term and I am getting, or I am defining another new function, new sum functions of the derived series, then the question is, can I conclude that your function G is exactly equal to derivative of your f? Because you see, I am having the new series which is nothing but the derivative of each term. Now the original series, if I add the each term, then it will have a sum functions f. So therefore the natural question, if I have the derivative of each term and it will give you another power series, and suppose the sum function is z, can I say that if I perform the derivative of the original sum functions f, the series of functions I started with, whether can I say that derivative of f is exactly equal to the sum function g, which is nothing but the sum function of your derived series? So this kind of questions you can ask, because each term you are getting the as a derivative. So because you have each term is n z minus z naught to the power n, and what is the derived series? Derived series, each term is the derivative of the term fn, right? So now in the left hand side, the original series you will have some functions. Now in the right hand side, you are taking the derivative of each term, you have the another power series. Now it will have a sum function because it is a power series. The left hand side, the original series of functions, it will also have a sum function because it is a power series. Now can I have any connections these two sum functions? Or in other words, can I say the derivative of f of your original sum function is exactly equal to your sum functions of your derived series of functions? Is there any relation? Answer is, let's see, I'll see the answers, whether this is true or not. That is one. And now see, the second one I am talking about 1 times differentiation, because these are all polynomials. But as I said, polynomials are infinitely many times differentiable. So instead of 1 time differentiation, if I take the k times differentiations of my functions, this a n z minus z naught to the power n. If I take the kth differentiation, then what will be the corresponding new series? This should be some factors will come out, then n into n minus 1 up to n minus k plus 1 times n, then you will have z minus z naught to the power n minus k. This is another power series, right? So there also I can talk about what will be the radius of convergence, and if suppose this is my radius of convergence of this power series, what will be the relations with the radius of convergence of my original series started with? Or now original power series will have a sum functions. Now this is a new power series where I am getting the kth derivative of each kind of functions fn. Now it will have a sum function g. Now can I say that, okay, like this kind of things, if I take the kth derivative of my sum functions, I will get back my original functions, or if I take the kth derivative of my original sum functions, can I have the sum functions of this series? So these are the questions you can talk about. That's what I'm saying. What about k times differentiated? If I instead of 1 time differentiation, if I take k times differentiation, what can I say? What can I say about the radius of convergence? What is the relations with the radius of convergence? Or what can I say about the sum functions of the k times differentiated series or the sum functions of the original series? Is there any relations? Or next question is that, is there any relations between the coefficients an and the sum functions f? You have a power series, and power series means the coefficients n are known. Now this power series will give a sum functions f. Can I have any relations of my coefficients n and the sum functions f? So these are the questions you can ask, and you will see later on you will have an appropriate answers, and I'll state it as a theorem. Yes, most of the conclusions are correct. That means what I'm trying to say is that if I start with a what is called a power series which is of the form n z minus z naught to the power n, then it will have a domain of convergence. Suppose R is the radius of convergence, then if I consider the one times differentiated power series, new power series, both radius of convergence will be same. Instead of one times differentiation, if I go for kth time differentiation, both will also have the same radius of convergence. Not only that, if I consider the one times differentiation power series and suppose this sum function is g, then I can conclude that if the original power series sum function is f, then if I take the derivative of f, it exactly give you what is my function g itself. So similar conclusion also true for kth other differentiation power series. And yes, there is a nice relations of the coefficients n and what is the sum function f. I can write my coefficients n in terms of my functions f. Of course, I will show that my function is analytic. So if I start with a power series, the sum function which is actually analytic functions. If I have an analytic function, it is infinitely many times differentiable, and then you will see I can write my coefficients n in terms of the derivative of f and the contour integrations of f. So I can have the expressions of n in terms of the contour integrations of derivative of f. First I have to convince you, yes, my sum function is differentiable. That is important. So therefore all the questions are this kind of questions you can ask, and all the questions you will see later on, you will have a positive answers. That means if I have a power series around a point z naught, then the corresponding sum function is differentiable. In other words, it is analytic. Then term by term differentiation will be possible. If I take the term by term differentiations of my series of functions, then the new power series will have same radius of convergence with the kind of initial power series. And each time if I take consider the what is called derived power series, and if the corresponding sum functions is g, then if I consider the original sum functions of my power series, then if I consider first time differentiation, then derivative of f is equal to that g. If I consider the second derivative power series, then when I can talk about the second derivative of f, it will be exactly equal to the sum functions of the power series, where each term is twice differentiable of the original function, and so on and so forth. So therefore later in my slides you will see answers of all the questions, okay, these 1 2 3 4 5, and you will see all will have a positive answers. So first conclusion is that yes, if I start with a power series around the point z naught, then it will have a sum function, and sum functions will also be analytic. That is very important. Okay, so this is the theorem. Maybe proof I will explain later. So this is the kind of I have combined all the conclusions, and this is the sum functions of a power series. I said it is analytic. So this is my theorem. You start with a power series around the point z naught. Suppose it will have a radius of convergence r, then if I consider the sum function which is f of z, n z minus z naught to the power n, first conclusion is that yes, this is an analytic functions on the domain of convergence of my power series. Number 2, for each k, if I consider the kth derivative of each term, and if I consider the power series of kth differentiation power series, then it has the same radius of convergence of my original radius of convergence of my power series. Not only that, if I have the sum functions f of the original series of functions, then if I take the kth derivative of f, then it will give you the sum functions of the derived what is called power series. That means derivative of f at kz, which is exactly equal to the sum functions of this power series. And what is that power series? This is the kth derived power series of my original power series. So that means f of kz, which is exactly equal to n from k to infinity, n up to n minus c, this is the constant term, times z minus z naught to the power n minus k. That means, or in other words, you can say that if I consider this power series, the corresponding sum function is exactly equal to kth derivative of f at z. And you see, as I said, the coefficients n will have a relations. Coefficients n, which is nothing but nth derivative of f at z naught by factorial n. Now nth derivative of f at z naught, now f is analytic. Now you can have the Cauchy's integral formula for derivative. Then you can have the expression of n in terms of the contour integrations of f on the boundary. So that is what I am trying to say. So therefore n, this is the relations of the coefficients n and your sum function. That means n is fn z naught divided by factorial n, and then also n I can write in terms of the contour integrations of my f on some contour. So this is the nice relations. So that means, in other words, if I give you some kind of functions and some functions, then I can explicitly calculate my what is called coefficients of my power series. Anyway, so these are the kind of conclusions of the theorem. So what I will do in my next lecture, I will prove partially of the results, because otherwise it will be very complicated. Okay, so I'll maybe for one time differentiation I will conclude you. Okay, first I will show that yes, the sum function is analytic, that I will do that. And for the second one, instead of kth derivative, I will just start with the first derivative, and then I will show that yes, if I have a first derived power series, then the radius of convergence will be same with the original power series. And in the first derived power series, if it has a sum function g, then g is exactly equal to f prime of z. What is f? F is the sum functions of my original power series. And kth derivative, it is actually follows from the inductions. And of course, I will show that yes, the coefficients actually of the form f and z naught divided by factorial n. In fact, it actually follows from here, number 3. So I think I should stop here. So these are the kind of proof. I will give the proof of this theorem partially in my next lecture. So that means if I have a power series, some functions will give you analytic functions. Now Taylor's theorem says the converse. If I have a analytic functions at some point, then it will have a power series expansion around that point. So Taylor's theorem is the converse of actually this theorem. Maybe I will discuss more on that later, but this is one of the theorem. That means if I have a power series, then we will have the analytic. Some function is analytic, but converse is actually the Taylor's theorem. If I have a analytic functions around a point or at a point, then you will see that will if I have a analyticity at a point, then it will imply it my functions will have a power series expansions around that point, and that is the Taylor's theorem. Maybe that will come later, but in my next lecture I will first start with partially. I am not giving the full proof of the theorem, I will give a partial proof of that theorem. That means I will show that my sum function is analytic, and instead of dealing with kth derivative, I will deal with what is called first derivative, and couple of properties I will talk about, and then here we will have Taylor series will come, and then Lorentz series. I think I should stop here. Next lecture I will start with the proof of this theorem, not fully but partially. I think I should stop here. Thank you.